Thank you. Welcome to this second talk of this afternoon. And for me, I'm very happy to have a chance to have Uwe Keller to give a 1 hour long talk, because he will say all the things he wanted to. And I just want to say that I met Uwe. If you remember, I met you must be in 1977 in La Jolla, when you in Colin came visit me and also Diana after your trip to Libya, the desert. And you were not telling us about anything about Comet, but about the desert itself. That's my impression, And by the way, Diana is online. She wants to say hello to you, but I think that since you need to start your talk, and anyway, so Diana, yeah, wait until Uwe sees you.
Hello, Diana.
All right, so many people are expecting, waiting for your talk. And Uwe, can you start? Oh, I should say that before he gets started, Uwe, is a really, I would say the senior member of the Cometary community, and he was PI of the Giotto camera, and so in fact he started he opened the first chapter of our modern understanding of comets. And so the title is From Giotto to Rosetta. Uwe, yes.
Okay, so we are ready to start, and I'm giving an introductory talk more or less to Cometary Nuclei, what we have learned about comets in the last 150 years. In the early times, I will be very fast, and more or less ending up with Rosetta. And afterwards, I will give a short lookout what the next missions are or might be. All of you may have seen a comet in the sky. It's a very weak appearance. Usually you have to have a good night sky, but comets as they appear on the sky can be very, very large and have very different forms. Like here you see an anomalous tail, which is a projection effect. This is a comet where you don't see a dust tail or hardly any dust tail, like here. This is a blue tail because it's the ion tail, ions driven away from the nucleus. Oh, what's that? Ions driven away from the nucleus by the solar wind. Dust is driven away, of course, by radiation pressure. And very often comets break up. And the breakup sometimes can be observed. That's probably the normal fate of a comet, is that it breaks up finally before it disappears. And comets can be very large phenomena covering the whole sky, and very impressive, of course. And the question is, how is this capricious appearance formed? Where does it come from? What is the source of this phenomena? And with time we found out that the source is a very small nucleus in the order of a few kilometers, maybe tens of kilometers, whereas the tails and the coma is typically 10 to 5 kilometers diameter in the coma, and the tails can millions and tens of millions kilometers be long. So this very tiny nucleus produces this interesting and beautiful phenomena on the night sky. So we, of course, were interested in what is the nature of this nucleus and what is the nature of comets itself. And the connection between comets and dust, so to speak, between comets and meteor showers was found by Schiaparelli in the middle of the 19th century. Then people started to model the dust tails which appeared, and found out that you have a repulsive force from the sun is needed. Finally, also closer investigations of Comet Encke, which has a very short period and can be often observed. It was found that you need non-gravitational forces to explain the changes in the orbit of the comet. This is already indicating that you have to have some sort of kind of body. Eddington, of course, found the fountain model. The fountain model, in the sense, the production rate is towards the sun, and then the dust is driven away from the sun, and it looks like a fountain. The connection, the importance of dust and connection to dust was maintained till the middle of the 20th century, when Little published his model of a sampling model, where the gas which has been observed is adsorbed on the grains. Of course, when spectrometer came in use, the interest shifted from the dust to the gas, which was observed with the spectrometers, and mainly the brightest emission in the visible part of the spectrum is Cn, and Cn is a radical, and it is observed in resonance fluorescence, as was shown by Swings. And the problem is you can't store radicals; they are too active in matter. So you have to find a way how to store the radicals. And the suggestion by Wurm was that radicals are stored as parent molecules. For example, Cn is stored as HCN and only dissociates once it's freed from the central body, from the nucleus. Whipple introduced his famous icy conglomerate model to explain the effects of non-gravitational forces found in comets. The model which is dominated by ices, and for various ices, a conglomerate, as the model says. And in the 70s, the first UV observation from satellites were possible. And then we were able to observe the comets, the hydrogen Lyman alpha resonance fluorescent line from in the far ultraviolet. And the water, of course, the hydrogen, of course, is a dissociation product of water, which dissociates in hydrogen and OH. And OH also can be observed. It can also be observed from the ground, but just barely, because the influence of the atmosphere. Then the other problem we saw at that time is that when comets come close to the sun, the activity usually starts at around 3 or 3.5 astronomical units from the sun, and the activity starts all together. That means we observe water, CO, and CO2 as more or less at the same time. And there was a question, how can it be? CO is so much more volatile than water. Why doesn't it show up further away? And the idea from DSM was that those minor, more volatile species are trapped as class rates of water class rates in the lattice of the water crystals, and to explain this effect. Of course, it was clear at that time already, by when the more volatile stuff was observed, that comets had to be stored at very low temperatures before they came into the solar system. And temperatures we are talking about are in the order of, let's say, 30 K and below. And therefore, it was clear that the comets had to be formed in the very early time and far out from the protosun during the formation of the solar system. So the hope was, and I think people were rather optimistic, that we can learn something about the starting conditions, the chemistry, and the physical conditions of the protoplanetary nebula while it was forming the solar system. And this is the overriding interest in comets, is that they are witnesses of the early formation time. So it was when Comet Halley came around. Comet Halley shows up every 75 years from a highly elliptic orbit. It's a and is a very active comet and has been observed over the centuries quite often already, starting I think 2000 before, or 2000 years ago, or more than 2000 years ago, in Chinese chronicles. And this gave a jump in our interest to investigate comets, and several missions were planned to do these observations. Comet Halley is not a very good object for observations because its orbit is retrograde, so the flyby velocity of spacecraft is adds the velocity of the Earth to the velocity of the comet, and the typical flyby velocities of all those spacecrafts close to the nucleus were in the order of 70 kilometers per second, very fast. We had two Vega missions passing a few thousand kilometers away, and then we had the Giotto mission, which passed about 600 kilometers away from the nucleus. And you can see that the approach to the nucleus was at high phase angles above 90 degrees. So during approach, the sun, the shadow side of the comet was visible, and the solar illuminated side would have been visible after the closest approach. The cameras on the Vega survived. The camera on the Giotto spacecraft was hit by dust particles, and it did not survive the closest approach. Therefore, the Giotto mission only produced pictures with high phase angles. But nevertheless, these pictures of the first pictures of a cometary nucleus changed our perception of the nuclei. From the icy conglomerate model, we found, in contrast to the icy conglomerate model, we found that the nuclei are very dark, containing dust, some ice, obviously because of the activity, and organic material. The nuclei had to be formed because of the large amounts of highly volatile CO and CO2 observed, formed and kept below 30 K. As I mentioned already, there was no water visible on the surface. That was to all our surprise, I think. The physical properties of the nucleus was rough and determined by non-volatile dust component. It showed mountains, cliffs, and so on. And this is quite different from a subliming icy conglomerate snowball, if you want this comparison. The refractory to volatile ratio was larger than 1. And before, people thought that it's a dirty ice ball. That means ice was prevailing. And we found, I think, that the refractory part was prevailing over the ice part. Cometary nuclei are bigger than required to produce the observed activity. This is clear, this is an outcome because they are very dark, and obviously the areas of activity are limited, or the production rate of subliming water is diminished by the amount of dust of a dust layer through which the water vapor has to diffuse. Because they are bigger, the comets had to be porous and of low density and low tensile strength, as So what did we observe? We saw, as I described already, a very rugged bilobal nucleus. The size is given down here. Here we go. The size is given here. And so it's obvious that there were ridges a mountain was visible, which may have been several kilometers above the enveloping ellipsoid of the body. And so it was clear that you could describe some of the features in geological, geophysical or geological terms, I should say. So this was the first observation of a cometary nucleus. This was in 1986. And about 15 years later, the next mission went to Comet Borrelly. It was a DS-1 mission, American mission. And the body of Comet Borrelly looked quite similar to what we had observed in Comet Halley. It looked also bimodal, and you clearly could also see geological features like ridges and mesas and whatever you want to call them, mottle terrain, pits, and so on. And this comet, in contrast to Comet Halley, had very low activity. I mean, a typical Jupiter family comet, short period comet, the activity of those comets are typically 2 orders of magnitude lower than the activity of Comet Halley. And this is why you don't see any dust around the comet here, because the exposures are too short. Only in a very long overexposed exposure you could see some dust activity, and it's obviously much lower than the activity of Comet Halley, which made Comet Halley also a very interesting object compared to a normal short period comet. So it looked, at that time, it looked so, comets are similar to what you saw in Comet Halley. The question is, how do you produce activity? That was immediately, already with Comet Halley, it was a question, how does activity work if you don't see any ice on the surface? So here the suggestion came up that you probably may have the activity only at the ridges formed by the mesas, where the gravity makes sure that the dust is easily removed from the underlying icy material, and the dust is not collected on top of it, so the activity could go on and eat up the mesa if you want to. That was one idea, but lots of such lots of ideas came up, and but they were difficult to confirm, and so everybody was interested in the following up mission by Stardust, where you had also a flyby, and here the comet was not bilobal, it was much more spherical and somewhat smaller comet, and again we saw an extremely rugged surface. It was clear that this surface is maintained by a refractory material and not by icy material. We saw ridges and spikes going up here, 200-meter high pillars and pinnacles. If you want to, you can see them here. Here again, the same pinnacle. You see ridges here and lots of crater-like pits, which are of course not craters, but they probably are formed by the activity. Going on, the next mission was an experiment, a deep impact to Tempel 1, Comet Tempel 1 in 2005. Again, a different form of comet, not so bilobal, but also not spherical either. And the interesting part was, of course, the experiment with the impactor, but the results from this experiment were limited. Other results from the flyby were quite interesting, particularly the first time some indications of icy material, some icy patches. And here icy means that a few percent of ice compared to the refractory material was found, just barely, but barely visible, and not sufficient, of course, to explain the activity, the small activity either. But the important parts are that it was confirmed that the thermal inertia was very small, and consequently the heat conductivity into the nucleus was also extremely small, and this is really important for the understanding of how comets survive and produce activity for many revolutions. So the conclusions from the first interactive experiment, in the sense the impact, you can see the impact on the right-hand side, is that comets are very low density, very weak. This is by modeling the impact here, but with large error bars, because the observations of the resulting crater was not very precise. We found, as I mentioned, very low thermal inertia, very low heat conductivity, and again, ice was not visible except for a few percent in some spots. So what are the consequences for the physics of the cometary activity? This needs to be modeled now, and you can see here that from the models by Prialnik, following the low conductivity, it takes only a few centimeters. The heat penetrates during a cometary day only a few centimeters into the surface. As you can see here, temperature versus depth for different hour angles, and at 3 centimeters, 4 centimeters, you don't see the daily variation anymore. The diurnal skin depth is a few centimeters. The orbital skin depth, of course, is larger. It's in the order of almost a meter. So the situation at active surface are diurnal skin depths in the order of centimeters, orbital skin depths less than a meter, and then you can calculate to maintain or to produce the observed activity, the amounts of dust and gas. You have to erode a certain amount of the surface layer of the nucleus, and you can make a calculation, and you find that you erode about 100 to 200 centimeters per orbit over the whole surface of the comet. And in active areas, of course, it would be more, and in inactive areas, less. The consequence of that is that the surface recedes faster than the heat wave penetrates. And this, again, means that the material a few centimeters below an active surface was previously covered, in previous orbits, covered by meters of essentially unaltered nucleus material, and is not affected by insolation. That means if you are looking into an active area, the surface of an active area, what you essentially see is pristine material, because it had been before the interior of the nucleus 1 or 2 or more meters below the surface. This is an important consequence, I think, for the question of how you can sample the nucleus, and how you can sample, how easy or not easy it is to sample pristine material from a comet nucleus. And as another consequence is that activity shows little degradation with cometary age. And this is confirmed, for example, with Comet Encke, whose production rate varied very little over the 40 or 50 apparitions we have observed the comet. And in other comets, it's also quite normal to assume that the next apparition, the activity is going to be the same as before, if the orbit is the same. Then we had a flyby of Comet Hartley 2 by the same spacecraft to a second comet. And this was what is called a hyperactive comet. That means a comet which has high production rates compared to the size of the nucleus, of its nucleus. And what was observed is that you have a strong activity here on this part, and this activity is not driven by H2O, by water subliming, but is probably driven by CO2 subliming. As you can see here, CO2, the spectrometer found CO2 concentrated in this area. On the other hand, it found water ice concentrated here. That means the interpretation is that the particles, icy particles, were ejected by the CO2 production rate into the lower Coma, and from there the particles follow, and particles were observed actually followed the gravitational forces. Partly, most of them were completely ejected, but some of them seem to fall back into the gravitational low area here, which is quite smooth compared to this rugged, rough area here. And so the first time the interpretation was that the fallback material from an active area to inactive areas is an important phenomenon on comets, and has to be taken into the sedimentary process, has to be taken into account when, particularly if you have comets where the activity is strongly influenced by CO2. So, summarizing the flybys, we flew by 5 comets and with 6 flybys by 5 nuclei, and you can see that about 3 of those comets from the 5 comets look bilobal. So this seems to be a typical way to form comets. They are formed by the slow collision of 2 subnuclei. If you want to, as you can typically see with Halley, Hartley 2, you see it Borelli, and you see it also in the Rosetta, which is the 6th comets we are observing. And this time we observe the comet not during a flyby for a very short time, but during a rendezvous, which started in 2014. The instrumentation was very powerful, covering the UV to the infrared. We had a instrument to probe concept the interior of the nucleus. We had a lander for super high resolution and imaging and thermal probing of the surface. And the idea was to follow a comet over the full cycle of activity. When the comet approaches the sun at about 3.5 to 4 AU, down to perihelion as 1.2 AU, and in a way again in the direction of aphelion. So this was a mission designed to observe activity and to understand and to find out how activity on a cometary nucleus really works. When we arrived at the comet, we were quite surprised by the shape of the comet, which clearly showed a very strong bilobal shape, where you have a smaller lobe on the right-hand side and a bigger lobe on the left-hand side, and between the area we call the neck. And you can see when we approach the comet from the northern part. The rotation axis comes out in the center and is very strongly oblique, 50 degrees oblique. And we saw the northern part, which is illuminated, while the comet is farther away from the sun. So in aphelion, we have northern summer. In perihelion, close to perihelion, we have southern summer. And you can see that the first surface, immediately the impression is that the surface is covered. It's partly very smooth. The underlying features are very rocky, very rough, lots of crater-like features, large ridges, and so on. And but the surfaces which had a horizontal orientation seem to be rather smooth and obviously covered by some grains or dust. And the roughness of this comet is really astonishing. If you think about the size of the typical size of this nucleus is 4 kilometers, and you are looking here at a wall which is 900 meters high. This wall here you can see is 900 meters high, falling down into the harpy region, into the neck. And just to give you an impression how what the low gravity environment looks like or feels like is shown here. Let's assume that you liberate a block of material with a density of 500 kilograms per cubic meter, and let it tumble down from the rim of the wall, and it will take 1 hour for the block to reach the bottom, down 900 meters. And if this block has a fresh surface, water icy surface, you can calculate the acceleration you get from the sublimation of the water ice, as given in this formula here. Compare the acceleration to the gravitational acceleration, and this is a pressure here of the water sublimation in Pascal, and the typical value would be in the order of 1. And then you can see that bodies up to 5 meters, the acceleration is comparable to the gravitational acceleration. That means the pressure, the water sublimation pressure, is high enough to propel the block of several meters, and the block could possibly leave the nucleus just by the sublimation pressure. In total, the gravity acceleration on the comet is 10 to minus 5 of the gravitational acceleration on the surface of the Earth. And on the other hand, the strength of the material which we observe and which we calculate for models is in the order of 1 to 100 pascals. And this is about 10 to minus 5, the tensile strength of Earth rocks. So you see that the ratio between acceleration and strength of material is about the same. And this explains why this comet very much looks like areas in the high mountains, the rocky areas where you have large walls, you have steep edges, and so on. This can be maintained or is maintained in the same way on the cometary nucleus, which we observe with Rosetta 67P, Schumacher. So this is not, as you can see, a picture of my last vacation. As you might see, it is really what you see is the rugged surface of the nucleus of 67P. Very similar in the morphology, in the topology, morphology, what you can observe on Earth in many areas. Now let's look at the activity. What can we say about the variation in activity with heliocentric distance? On the left-hand side, you see the northern part of the nucleus indicated as the rotation axis here, perpendicular to the screen. And the right-hand side is the southern part, and a calculation of the total amount of production. And you can see that on the northern hemisphere, even though the overall illumination or energy absorbed is quite similar to the southern part, the production rate is only 20% of that what is produced on the southern part. The southern part gets much hotter, and production rate is, of course, highly nonlinear, changing with temperature. Therefore, during the perihelion here by the black curve, the subsolar latitude is given here as more than 50 degrees. So you see during perihelion, you have strong southern summer, and this provides a quite different production on both of the sides. The south is eroded, rough, and part of the material is located onto the north. And this produces this dichotomy between the north here and the south side here, as you clearly can see. And this is due to the transport of material and, of course, to the fact that there's less, at this stage, at this orbit, there's less production on the northern side than on the southern side. But I think the roughness is indicating that at some other time, the orbit was different of the comet because and we know that the comet passed Jupiter some 2 or 3 orbits before. So the orientation of the spin axis may be was different, and the northern part got more sublimation at that time than it is getting now, I guess. So just to see, demonstrate this again, the different appearance, the harpy area, the northern part, smooth area, this was already mentioned by Marco earlier, and then the south part, where you can just sort of give you an impression of a rocky area, where the more or less pristine material of the nucleus sublimes during perihelion. And we see big pillars, we see cavities, and here, for example, 15-meter deep cavity, and this can be used to calculate the strength of the material above the cavity, and this was used to give you the values between, let's say, 10 and 100 pascals. You can see small pillars, similarly what we have seen in earlier flybys, and cometary surfaces are really a geologist's delight. Lots of different features to investigate, collapses of walls, which we observe, taluses, and so on and so on. And clearly, if you model, you can see that the cliffs, which are shown here, produce more highly productive than the smooth surfaces on top. And this just indicates that the cliffs are eaten up by the erosion. Dust is not only fine dust, as is generally observed in the tails, and but we also saw that there are bigger chunks. The camera could observe particles in the order of decimeters, up to decimeters, from active areas, and follow the trajectories here. And you can see that some of the trajectories are turned down again towards the nucleus. They are flying up towards the sun, but then you can see that there's a force acting from the sun towards the nucleus, and this is explained by the fact if the particles are active themselves, if they sublime water or CO2, then they would produce a force towards the nucleus, because sublimation mainly takes place towards the sun. So this indicates that that also large particles are lifted from the surface, and the question is, how do you really do this? How do you lift decimeter-sized particles, meter-sized particles, which with very low pressure, just from sublimation of water ice? Here you can see bigger particles, meter-sized particles, between the nucleus and the spacecraft rotating, and you can see how it moves away. And there's a second smaller particle also, and just giving you a direct observation of these large pieces. And we know, and you have seen this in the very early images I showed, that much larger particles break up and can sometimes be observed. The question is, how do you do this? The activity is everywhere. When the sun shines on the nucleus of 67P, the nucleus is active. Whether it's covered by the dust, or it's the pristine side from the more pristine side from the south. Whenever the comet, whatever is illuminated by the sun, shows activity. That means also the dust, fallback dust material, contains water. It is wet. This shows that the jets, or what you may streamers you see, are really not inhomogeneities of the surface. The surface is homogeneous. All the surface produce more or less the same amount of dust if it's illuminated with the same insolation. And the streamers are formed by the topography, by the morphology of the surface. And as you could see in this model calculations, and So the impression you get and what we see is that the overall activity on the surface is more or less uniform and homogeneous, except for the phenomena of the dust jets or outbreaks. We observed several tens of outbreaks, some larger, some smaller, which the physics of it is not very well understood. They are very concentrated and limited, very short term in some sense. Here, this is an example where the outbreak only lasts less than, I think, 20 minutes or so, outbursts between 1705 and 1720. So what did we observe at the beginning when we approached the sun, the nucleus? In the coma, the composition of the coma, we saw that on the northern part, the composition was dominated by water, and only very little CO2 was visible on the northern part, and water was north because it was illuminated. The south was not illuminated or very barely illuminated, therefore no water production, but the CO2 production was concentrated on the south and hardly any CO2 on the north. And this goes along with the fact that the north is covered essentially by the fallback material, and this fallback material is more or less depleted from CO2. And the original cometary surface has much more CO2 on the south than on the north. You see also a dichotomy in the coma, not only on the nucleus itself. So the activity pattern of 67 is very complex, even though it comes from a more or less uniform surface and is controlled by the season. So the fact that season can play an important role in cometary sublimation has become obvious and needs to be taken into account in the interpretation. Around perihelion in the southern summer, observed pristine origin in nucleus material, more or less. A considerable mass fraction is eroded into large particles, centimeter, decimeter, and meter size even. Nevertheless, the surface is found chemically uniform. Likewise, the interior is homogeneous. Both slopes are identical. There are a lot of investigations to find differences and show inhomogeneities, but if they exist, are rather small and very difficult to discern. So let me now go from the physics of the cometary nucleus to the chemistry of a comet, and there the point is one of the important parameters observed is the D2h ratio. This was already discussed also by Marco, and the D2h ratio of 67P was very high, namely 5 times 10 to minus 4, about 3 times as high as what you find on the Earth. Also, the doubly deuterated water was rather high, and the ratio between those two components is about 17, and in simple equilibrium you would expect only 0.25. So it is clear that the material the chemistry did not go on in thermal equilibrium. If you're on the left-hand side here, you see the D2h ratios of various comets. And before 67P, the idea was that the odd cloud comets had a higher ratio of D2A because they were produced further away from the sun. And the short periodic comet had a lower ratio because they were produced closer to the sun. But 67P showed that this is not really true. And now one assumes and thinks there are strong indications that all comets are essentially formed about a certain range in the protosolar nebula. And then there are dynamically separated. They are produced in more or less the same area, but then the dynamics of individual comets were quite different. Many of them were thrown out into the Oort cloud. Some became, after several steps, short periodic comets. But the physics and the chemistry of the comets are not very different. So I think the conclusion is that the Earth did not get the bulk of its water from comets because the D2h ratio doesn't fit. The high D2h in alkenes and H2S and other NH3 and so on point to a pre-solar origin. And the D2h in methanol, for example, which is depicted here in ratios, is very similar to what you found in proto-star regions, as you can see in this diagram here. This is the conclusion from the Rosina observations produced by Altweg et al. And we have several hints for non-homogenized protoplanetary disk and unprocessed pre-solar material. There is a strong mixture or some mixture of material in the protoplanetary disk, as already indicated by Marco and is indicated by many models, and also found from the laboratory investigation of stardust, where you find, Marco talked about this, I don't have to go more explicit. The Rosetta shows that the xenon isotope ratios are non-solar, the silicon isotope ratios are non-solar, sulfur isotopic ratios differ among molecules, but the bulk is non-solar. We talked about the D2h ratio, and it is compatible with direct heritage of water ice from pre-solar disk. Presence of very volatile S2, which has a very short lifetime, requires pre-solar ice. There's a good correlation between O2 and H2O observed, requires again pre-solar ice. So the conclusion is mixing in the solar protoplanetary nebula was inefficient at the location of comet formation. Mixing in the protosolar, as I mentioned, is inefficient. There was mixing very clearly, but it's not efficient. It's not fully mixed, completely mixed up the material. The protosolar nebula chemistry was probably not the main chemistry process in comets. Prebiotic molecules, salts, non-solar isotopic ratios point to a rich pre-solar chemistry. So this is all for the just a very brief summary, I think, of what we have found out from the vast amount of information collected by Rosina, and the interpretation is still going on. It's going to take another few years to really get all the fine information out of the spectra. So how does the Rosetta mission compare to the Flyby missions we have seen before? Of course, Rosetta determines the physical properties of the nucleus with a very high accuracy, like shape and mass and density. The seasonal activity variations found out that the seasonal activity variations can be dominant. Many of the surface morphologies observed by the Flyby missions, and as you saw, could also be found on 67P on different parts of the nucleus, so to speak. There are the smooth areas, there's the very rough areas, and so on. This suggests, to my mind, that the diversity of nuclei is a consequence of the evolution of intrinsically similar and homogeneous bodies. Look, comets evolve differently, but they started up with more or less the same composition and material. The refractory to volatile dust to ice mass ratio has been under debate from 1 to 9. But I think recent models clearly suggest that the ratio is somewhere in the order of 1 and small, and some, or maybe somewhat larger than 1, but clear near to 1. This may be in contradiction to some, or is obviously in contradiction to some other opinions. Low temperature supervolatiles confirm the formation and storage in the outer solar system. I think this is a clear, strong evidences, consequences from the observations of Rosetta. The details of the things we had to observe are not so straightforward. Many observations have big error bars and are supported only by modeling, which is not necessarily correct. The shortcomings, I think, from Rosetta is that the restricted operational performance of Rosetta, requiring continuous flybying and terminator orbits, severely limited the systematic observations. I mean, we had been 2 years at the comet. Distance to the nucleus was too large. It was considerably larger than anticipated. In the beginning, it was tens and hundreds of kilometers rather than a few kilometers as originally promised. No reliable and systematic surface temperature measurements were done. This is a major drawback. We had no certain measurements and variations of the temperature and the variation of the temperature. This is where you find out about the properties like heat conductivity and of the material, and this has large errors and very difficult, and could only be received at certain parts of the nucleus, but not overall, and mainly because we had no instrument really to cover low temperatures. We are missing, had been missing a bolometer. And as a consequence, the key question, to my mind, has not been answered yet. What are the physical processes and parameters controlling cometary activity? How does it work? I think, for me, the Rosetta mission was designed for a 2-year follow the activity from onset to decay via the perihelion, was designed to answer this question, and I think we don't know yet. There's no unique model which really describes the activity. Even so, we have a large amount of data, 80,000 images and hundreds of thousands of spectra from Rosina. So this is still material to be working on. Now, let me end up this talk by giving you a very brief outlook what's going on right now in cometary missions. And here I have to mention the Chinese Tianwen-2 mission, which has been approved and is supposed to launch in 2025, going to a near-Earth asteroid, and then sampling the near-Earth asteroid, bringing back the sample to Earth and flying on to Mars and a flyby to reach main belt comet 311P. And this is a very demanding mission, I think. If it is successful, it will be a major milestone in interplanetary missions to small bodies. So this is going on the Asian continent. On the European continent, we have a mission approved by ESA, which is Comet Interceptor, and which wants to fly by a dynamically new solar system object. The idea is to store the spacecraft after launch in the L2 point and have the spacecraft wait until a new comet comes into the inner solar system, then reactivate the spacecraft and try to fly by this new comet. So this is the only possibility to look at the differences between new comets from the orbit, from far away orbits, compared to the comets we usually observe, the Jupiter family comets. This mission has three spacecraft, one major spacecraft, one smaller Japanese spacecraft, and so the three spacecraft are flying by in different trajectories, so that 3D information can be gained during the flyby. And the purpose is to find out whether there are systematic differences between new comets and so-called new comets and the periodic short-periodic comets. Beyond those missions, there are lots of proposals for missions in America, and but none has been really selected so far. What are the different concepts? You could think about a Coma swarm, where you have multiple satellites flying towards the comet, as similar to the last mission I said, flying by and try to get 3D information. You have a surface network. You can land several small packages on the surface and analyze the various parts of the surface. You can, instead of many packages or several packages, you can land a surface rover, which the rover on the Cometary nucleus is not a trivial thing, as you have seen. In some parts, you can maybe use a rover easily, but then this is not very interesting because the area doesn't really change. The rest is obviously very rough, not so good for rovers. You can have a single spacecraft flying by various numbers of comets, which has been already proposed in the States. You can try to have an advanced exhumation. That means a deep impact, but now deep impact controlled by an orbiting spacecraft rather than just by the flyby where you barely can see the crater. An orbiting spacecraft, you can investigate the crater in very detail, and this learns much more and constrains the parameters much more than it was possible during the deep space experiments. Of course, I think the real thing to do is the comet sample return. You have so much more possibilities to analyze data in the laboratory than you can do in situ, and you can do this for many, many years with very small amounts of data. Look at stardust, where you have milligrams of cometary material and tens of papers investigating this material, and lots of surprises came out. And if you now have kilograms of material, you could determine the age of the material, which is a very important figure to know. And this is possible by a sample return, not necessarily at cryogenic temperatures, but what I suggest, and what we have already suggested several times, is to take a sample, keep it cool, let's say around 100 Kelvin or 120 Kelvin during flyby, and keep it at this temperature, put it in the laboratory, and then the water ice is still going to be ice, and in the original configuration, the more volatile stuff will be gases, but we will learn a lot of the structures, the refractory material, about the material itself and the age of the material, for example. And this is a much easier mission than the sample return at cryogenic temperatures, which is much more difficult and demanding. So my suggestion is make a sample return and require the sample to be as cold as possible, rather than telling it has to be below 70 K or somewhat like that. And this may be a possibility for the next big step in cometary research. And of course, we had a chance and tried with Rosetta to understand the activity. And what I really would have liked to understand is, how do you put a block of meter-sized block on top of this rough terrain? How does this work? How does activity do this? This is I think, what I would have liked to learn from Rosetta, and I have to say I didn't learn it, and this is why I'm somewhat, as Marco said, disappointed about the Rosetta mission. So thank you very much.
So Uwe, thank you so much for this detailed lecture. Any question from the audience? Let's see. Any question? You could raise your hand. Okay, we have a student, Lin Chi Hong. Yeah. So ask your questions, please.
Okay, so can you hear me okay, Professor?
Yes. Yes.
Okay, so I have few questions for you. So the first one is because we know the principle of rockets is to eject the air flow and to push the rocket fly. So my question is because it is the jet flow in the comet surface is very large. So is that possible that the comet their surface jets to change their orbit? Is that possible, especially in a small comet? So this is the first question.
The orbit is changed by the sublimation of material, not so much by the jets you see, because they are very limited. The speeds are not so high of the material, and therefore, but they are changed by the sublimation itself. And this was an important fact to understand that comets, comet nuclei exist. And actually, we are right now still working on the question what we can learn from the change of the non-gravitational forces onto the nucleus of comet 67P. We observe the deviation from Kepler orbit and can calculate this activity and compare this to the observed non-gravitation of the deviation from the orbit.
Okay, so my second question is because you mentioned about this the jet flow, and maybe it's origin from the after landslides later the exposures of the volatilized substance. So my question is because in theory this kind of substance, this is a solid, so it cannot be flow. So after the local substance that release the all volatilized gas and chemical material later, will this part of the local jet flow be stopped, or the gas will still be continuously flow into the point come from the other part of substance? So this is the second question.
If I understand you correctly, you want to know how can the activity be maintained on the surface, and the only way to maintain the activity of the nucleus is you have to remove the non-volatile material. From the volatile material, the ices, the subliming ices, have to be capable to remove the non-volatile part, the dust. And if in the moment the the sublimation can't remove the dust anymore, the comet would be dead. The activity would die. And this is actually the key question: is how does this really work? That you remove the non-volatile part by the sublimation. How is the physics? What is the physics behind that?
Okay, so my number 3 question is so because in theory this kind of volatilized substance still has a highest percentage of the size. This is made by volatilized material like a gas or ice. So after this kind of substance, they release all the gas and the water ice out later. Will their inside become loose and become fragile or easily to crush it down in a common surface? Will that happening?
Say this again. I'm not sure that I understand your question.
Oh,
Can
sorry.
you ask again?
Okay, I'll repeat again. So we know the volatilized substance in a comet's inside. So it has maybe it's the 10% or 20% their size. This is made by the gas or water ice. So after this substance, they release all the ice and the gas into the space later. Well, this kind of substance inside appears the pores or something in space, or to make this substance become fragile and crush it.
Yeah, but if I understand this correct, when you sublime the ice out of the pores of the dust, if it's a mixture, then at the same time you have to remove the dust. So the ice cannot, the material on top of the surface cannot be iceless, because then after a very short time, you could not remove the dust anymore, and then the activity would stop. Because as I said, I showed in the talk, the skin depths, the daily skin depths in the cometary materials is in the order of a few centimeters. And even the skin depth of over an orbit is only a few meters. Therefore, the heat does not penetrate deep into the nucleus at all. There is a question, and actually there is a paper where you can consider the fact that if you have higher pressure inside the porous material, higher pressure, for example, by subliming CO2 or CO, then this higher pressure, of course, goes outwards, but also produces a pressure inward. And this pressure inward could possibly crush some of the pores and compress the material somewhat. There are some discussions about this effect, but whether this is really taking place, I don't know.
Okay, thank you. The one question I have to both of you is that what do you think of the 67P? Is it really pristine, or is it a product of corrosion or fragmentation?
Yeah, I mean, it's going to be much shorter than Marco's. I think the observation, to my mind, of 67P showed that it has been formed of two sublobes, if you want to, by a very gentle collision of those lobes, and the density of the material is so low that major collisions, which lead to a compression of the material, can be excluded, I think. So formation of the cometary nuclei is by accretion, more or less, and then possibly very gentle collision of rotating lobes, and not by impacts. So this is my conclusion. And the things Marco alluded to, I think this is a typical problem of cometary physics. I think we have a lot of ideas of principles how this could be how things could be working, but we do not have the necessary confining measurements. Even this is also true, I think, for many measurements of 67P by Rosetta. The error bars and interpretation possibilities are still very large. That's the conclusion.
Okay, good. Yeah, good conclusion, Uwe. We need to have more. We have to work harder and more.
That's right.
Right. I hope to see you too, soon, either here or in Europe. And then once the pandemic is over, and we have now it's pretty late. I mean, late in the sense that it's 15 minutes past 5, and means that you have done your work. Thank you so much for for your both excellent lectures. Okay, right. Uwe, thank you. Marco, thank you, and everybody.
Yeah, thank you very much. Thanks for the invitation. And,
hi, Uwe.
Hi, Marco. See you later. See you next time.
Yeah, see you in Braunschweig.
Yeah, that's a good thing. Come and see us. Yes.
For sure, for sure.
Good.
Bye-bye.